Okay, so like we said, we're going to be doing more of this calculus of residue stuff. So let's start off. It's basically sort of like a gigantic bag of tricks. Okay, so we'll start with probably the simplest trick. Trick number one. So trick number one is pretty straightforward. Just recognize the integral as exactly the value of a contour integral. Okay, and here's the setting. You're going to have some function. You have some integral, say, of some function of sine theta and cosine theta. Okay, from 0 to 2 pi. And what you do is a simple change of variable. You say, well, look, you realize that if we let z be e to the I theta, right? Cosine theta plus I sine theta, right? Then you can, whenever we see a cosine theta, that's the same thing as 1/2 z plus 1 over z, right? Because 1 over z is going to be e to the minus I theta, so it's going to be cosine theta minus I sine theta, right? You add those two together and you get 2 cosine theta, right? So z plus z to the minus 1 over 2 is cosine, right? Z minus z to the minus 1 over 2i is going to be the sine, right? Sine is 1 over 2i, z minus z to the minus 1. And d theta is dz over ic, right? Because if you take dz d theta, right? dz d theta is going to be ie di theta, which is iz, right? So dz over iz is d theta. So that's your change of variable thing. You say, okay, so you recognize that whatever this real integral is, it's what you get when you evaluate a contour integral. When you evaluate a contour integral around the unit circle, right, of the same function for z plus z inverse over 2, z minus z negative 1 over 2. d2i, okay, and then d theta, which is dz over iz. So you can transform your real integral into a contour integral, and maybe if you're lucky, you can evaluate this contour integral using some residue, using a residue. Okay, so this is the simplest trick, and so for example, somebody gives you something like this, 1 over 1 plus 3 cosine squared theta d theta. Okay. And you say, okay, well, I'm going to write this as the integral over the unit circle. So the integral over the unit circle of 1 over 1 plus 3 z plus z inverse over 2 squared dz over iz. And if you work this all out, if you simplify this, then it turns into the integral over negative 4iz of negative 4iz over 3z to the 4th plus 10z squared plus 3. Okay. So you work it out, it turns out to be something like this, right? Okay. And then what do you do? What do you do with this? got the unit circle, we're integrating on the unit circle. So our concern is, where are the poles, right? So, so you'd say that, well, look, this is actually, how would you solve this? This is actually just a quadratic, right? This is a quadratic in z squared, right? So, solve the quadratic, you see that b plus z squared plus 3 has solutions at z squared equals -5 plus or minus 4 over 3. And so one has the simple poles. So the poles, and they turn out to be simple, which lie in the unit circle, are the roots of z squared equals minus 1/3. That is to say, z is plus or minus I over root 3. So those are the roots. Right, those turn out to be the roots, and then you just need to find the residues. Right. So okay, so we need to find them. So let's find the residues. Over root 3, right? We have this negative. We have this function, right? This 3z to the 4 plus 10z squared plus 3, right? And we'd like, it'd be to find the residue. It'd be nice to express this as your analytic function, which doesn't vanish at I over 3. Times 1 over z minus I over 3, right? Because once you get it in this form, then you just need to the residue is then you just take the function and then you evaluate it I over 3, right? By the result that we had at the end of class last time. So, maybe one way to do it is to just multiply both sides by z minus I over root 3, and then take the limit as z tends to I over root 3. Okay. So just evaluate the limit as z goes to I over root 3 of -4 I z minus I over root 3. 3z to the 4th plus 10 z squared plus 3. So here's one way you could go about it. This function is going to be analytic, so let's just take the limit as z goes to here. Now when you take this limit, you get 0 over 0, right? But you have L'Hopital's rule, so you apply L'Hopital's rule. By L'Hopital's rule, you end up with, when you work it out, it ends up to be -4i 2z minus I over root 3 over 12z cubed plus 20z. And then you just evaluate it, and it turns out to be -I over 4. You could just as well have avoided L'Hopital's rule and said, okay, I'm just going to factor this thing, and then take out this term, and see what phi of z is, and then evaluate phi of z there. That's fine. That would work just as well. Okay, but you know, just for amusement, let's do it this way using L'Hopital's rule. Right? This was in a book. I wouldn't have thought to do it this way. I would have done it the sort of, you know, like, I would have just factored this thing and then plugged in. That's more straightforward. But yeah, why not use L'Hopital's rule for fun? Okay. So then similarly at negative I over root 3, one gets the residue turns out to be, again, negative I over 4. So putting it all together, our integral turns out to be what? Well, it's going to be 2 pi I times the sum of the residues. Right? So negative I over 2. So that's pi. Okay. Any questions? Shall I give you one to try yourselves? I'll give you one to try yourselves. At least just to set it up.
Sorry, how do you get from the residue to the?
Well, you've got the residues, right? Here are the residues. Right? Here are the residues. What's the integral of your function around that curve? Well, 1 over 2 pi I times the integral is going to be just the sum of the residues inside. The residues at each of the poles. Right, but there are 2 of them. Right. This is the residue theorem. Right. This is the residue theorem. You know that this integral is going to be the sum of the residues. So it's a residue theorem, and so the integral itself is going to be 2 pi I times the sum of the residues. Okay. Another one, the integral from the degree of 2 pi of cosine 2 theta over 5 minus cosine 4 cosine theta. Well, at least take, say, 3 minutes and see how far you can get on this.
Is the identity for cos 2 theta, is that 1 minus sine squared theta?
I don't remember. What is it?
Wasn't that cosine squared theta is 1 minus sine squared theta?
2 cosine squared theta minus 1.
What?
2 cosine squared theta minus 1.
Is equal to cos theta?
Yeah.
Oh, so wait,
maybe let's just get started on it, because I think there's not really too much complicated about this, right? It's just you just do it. So if you don't remember your trigonometric identities, one thing you could do is say, well, I'm going to let z be e to the I theta, and then z squared is e to the I 2 theta, right? Which is cosine 2 theta plus I sine 2 theta, right? And then you can just use the same thing as before, right? Z to the minus 2 is going to be cosine 2 theta minus I sine 2 theta, right? So z to the minus 2 is cosine 2 theta minus I sine 2 theta, right? And so cosine 2 theta you can write as 1/2 z squared minus plus z to the minus 2. That you can do that if you don't remember. Okay, so same thing happens, right? You get so 1/2 z squared plus z to the minus 2 over 5 minus 4 1/2 z plus z to the minus 1. Oops. dz over z. And then basically the same sort of thing happens, right? You work this out, you do some simplification. It turns out to be something like this: I times z to the 4th plus 1 over 2z squared times z minus 2 times 2z minus 1. Easy. Right, and you see what poles you have to worry about, right? Only at 0 and at 1/2. Right? This pole is outside, so you don't have to worry about it. So calculate the residue as 0, right? Well, there's a double pole at 0. So when we find our phi, we need to take the derivative of it and evaluate it there. Right? Remember, the thing is that depending on the order of the pole, you take the n-1th derivative, you evaluate it at the pole, and divide by n-1 factorial, right? And that will give you the residue of the pole, right? This was. If you don't remember, this is what we did at the end of class last time. So you say, okay, well, I'm going to take my phi, then is going to be everything else. So I times z to the 4 minus plus 1, 2 z minus 2, 2z minus 1, right? And you take the derivative of that and you evaluate it at 0, and you get some number, which I think is 5 out of it. You get some number. I don't care. Okay, so then what else do you need to do? You need to calculate the residue at 1/2. Again, this time it's even easier. Right? You take your phi. Right, this is going to be z to the 4 plus 1 over 2 z squared z minus 2. Right. And then we need another 2. So 2 squared. Right. And then you just evaluate that. You evaluate that at 1/2. And whatever that number is, that's the residue. You sum the residues, multiply by 2 pi I, and that's the integral. So this trick is sort of the most elementary of tricks, right? It's simply, do you know what your contour integral is when you evaluate it, right? And when you see something, you say, okay, well, this arises from the evaluation of some contour integral. And you write down the contour integral, and then use the residue formula to evaluate the contour integral. So this is maybe the most basic of tricks. So we'll go on to some more interesting stuff, much more interesting stuff in a second. Okay. But are there any questions so far? Okay. So more interesting is the evaluation of improper integrals. So so let's just remember what improper integrals were. When we said something like this in calculus, when we said the integral from 0 to infinity of f, what we really meant was the limit of the integral from 0 to b of f as b tended towards infinity. Right? That's what that meant. Right? It doesn't, it's not, it's not like you can evaluate at infinity, right? But you take the limits of these finite integrals as the right endpoint tends towards infinity. Right? And that might not exist, right? But it could be that this integral, doesn't converge, right? Maybe this integral is infinite. But if this limit does exist, then you say that this improper integral exists and equals that number. And when we wrote something like this, what we meant by it was the limit as a went to negative infinity of the integral from a to 0, say, of f, plus the limit as b goes to infinity of the integral from 0 to b of that thing. So we, for this integral to exist meant that two improper integrals existed. Right? Each of these limits exist, and you take the sum, you get some value, you call that thing the integral from negative infinity to positive infinity. Otherwise, it's not really clear what this means, the integral from negative infinity to positive infinity. Right? Does it mean that you take first, you could say, I'm going to let both endpoints tend to infinity simultaneously, right? That could be one definition. Or you could say I'm going to let first I'm going to let this thing go to infinity twice as fast as that one, right? What does it mean? It's not clear just looking at this, but this is what we mean when we say. Okay. So we define these things provided that the limits existed. Okay, so note that if both limits do exist, if in the second one both limits exist, then this thing on the right-hand side, we could write as the limit as r goes to infinity of the integral from negative r to 0 plus this integral from 0 to r, okay, which is the limit from negative r to r of f as r goes to infinity. Okay, so if the limit exists, if both these limits exist, one way of evaluating it is to take the integral by taking both limits going to infinity at equal speeds. Okay, but it's not true. The opposite isn't true. This limit existing doesn't mean that these limits exist. Doesn't mean that these individual limits exist. So, for example, the opposite isn't true. It's not true. If you look at the integral of x from negative r to r, right, that's 0, right? And so the limit as r goes to infinity of this thing is 0, right? But the limit from 0 to b as b goes to infinity of x doesn't exist, right? Nor does the limit of x as you go from negative 1 to 0, right? Neither of these, as n goes to negative infinity, right? So neither, right? This is the integral, right? The integral, the area under y equals x, right? This is the, this is going to give you some huge negative number, right? So neither of these limits exist, but if you integrate symmetrically, then you always get 0. Okay, so again, if this limit exists, then you can evaluate it in this way. But this limit existing doesn't mean that that the integral converges. So there's a name for this sort of thing. It's called the Cauchy principal value. So we find the Cauchy principal value by one writes this PV is defined as the limit of the integral over that symmetric integral around the origin. So this is something that could exist even though the improper integral doesn't converge. Okay. If the integral does converge, then this will give you the right value. Okay, but it'll also give you values sometimes when the integral doesn't even converge. Okay, like in this case, you got 0 even though the integral from negative infinity to infinity of x is divergent. Okay, and one small comment. Of course, if f is even, then the existence of the principal value integral is going to be the same thing as the limit. That's twice the limit as r goes to infinity of the half, the integral from 0 to r, and thus implies convergence of the improper integral. Just a double. Right? Because if you're even, right? If you're even and the principal value, thing exists, well then, this is twice the integral from 0 to r. Right? And so that means that the integral from 0 to r as r goes to infinity exists. Well, that means that that each of these integrals, which are equal to each other, converge, right, as you go to infinity. Yeah, Christian.
But wouldn't that mean that you could integrate like x squared over the entire domain and get something finite? Because x squared would be even.
Yeah, it's even, but the principal value of x squared is going to be infinite.
Ah, okay. So the principal value just happens to be finite.
Yeah.
Oh, okay.
So the existence, like the finite existence. if you end up with some finite limit, then that means that this limit was finite, and that means that the improper integral converges. Okay. Okay, so now is trick number 2. So realize the real integral as part of a confident integral. So, okay, so here's the example. Somebody asks you to evaluate the integral dx of x to the 4th plus 1. Now, what do you say about this integral? Does this integral converge just from your knowledge of calculus? Just from your knowledge of calculus, does this integral converge? If you think about the function, right? The function, at 0 is 1, right? And then, basically as you head off here, then it's basically like 1 over x to the 4th. Right? It's like 1 over x to the 4th. Well, you know that for p bigger than 1, this integral from 1 to infinity is going to converge. The p-test from calculus, right? So, and here you don't have to worry because your function is finite here, right? So you basically have some finite number. You know that the integral from over here is finite, and you know the integral from over here is finite because of the p-test, right? And so, so you know that this is a convergent integral. So, calculus knowledge. Basically, the p-test implies that this integral converges. So we're going to evaluate it by using the principal value integral. Okay, this is an even integral, so we know that this is going to be 1/2 the integral from negative infinity to positive infinity. It's going to be half that. Since the integral converges, we know that that's the same thing. That'll be 1/2 the principal value integral of this thing. In other words, 1/2 of the limit as r goes to infinity of negative r dx over x to the 4th plus 1. So our concern is to evaluate integrals of this form. And what we're going to do is we're going to play a trick. We're going to say, let's pretend that we're in the complex plane. Right? Let's realize that we are in the complex plane. So we are evaluating the integral of some function on this path here, right? So what we're going to do is we're going to throw in another path. So right now our problem is to evaluate this integral. Well, let's throw in another piece here. Okay. So this total path we're going to call gamma sub r. Okay. And this top path We usually call it C sub r. Okay. So what's the idea, right? The integral dz of z to the fourth plus 1 over gamma r, we can get, right? How can we get it? By using the residue theorem, right? So we'll get that this is going to be 2 pi I times the sum of the residues. I equals 1 to whatever. Right? So by the residue theorem, you know that this is going to be true, right? But this is the same thing as the integral of the function over CR plus the integral that you're interested in. Right? Okay. So the integral that you're interested in, you can evaluate as 2 pi I times the sum of the residues, right? Minus this integral over the upper hemisphere, upper semicircle. Okay. And what we'll see is that we can, if your function satisfies certain conditions, then as r tends to infinity, this is going to tend to 0. Okay. So as r tends to infinity, what you get is that the principal value, so this is going to tend to 0 as long as something happens. Right? As long as, in this case, we'll do it directly. We'll see that we can bound this thing, and then the bound goes to 0 as r goes to infinity. Okay. So in the end, what you get is that the limit as r goes to infinity of this thing, that's say the principal value integral, right? Just equals 2 pi I times the sum of residues. Okay, and so that will, 1/2 of that will be our integral. Okay. Now let's put this together. So, so the two things we need to do. One is find the poles, right, and evaluate the residues. And 2, we need to get the bound on, show that this thing goes to 0 as r goes to infinity. Okay. Okay. So, okay. So, we're at poles, right? Z to the fourth is minus 1. Z to the fourth is minus 1. So, right, so you end up with fourth roots of -1. Right? So that turns out to be things like this, right? E to the I pi over 4, e to the I 3 pi over 4, right? This one, and then there are two underneath, but we don't care about those because they're not inside of our curve. So. So now we need to evaluate the residues. This time we're going to use the P over Q trick, because right? You have simple poles, right? So remember what the P over Q trick was. You have P over Q, and P of Z naught was not 0. Q of Z naught was 0. Q prime of Z naught was non-zero. Then the residue at Z naught was P of 0 over Q prime and z is, it's p and z naught over q prime over z naught, q prime over z naught. Right. So that's the trick we're going to use this time. Right. Your p over q is 1 over z to the fourth plus 1. Right. And so, right, so the residues are just 1 over 4z cubed. It's going to be right, at these two places, z1 and z2. It's z1.
Question. How do you know that the poles are simple?
Because they are, you've got these fourth roots of unity, fourth roots of negative 1, right? And there are four of them. Right. So you know, it's going to be, this is going to factor as z minus z1, z minus z2, z minus z3.
Okay.
There are four different roots, and that's just the nature of roots.
So you're just, whenever you're thinking of the order of a pole, you're thinking about if you factored out that
Yes.
that little linear term, the power that it's to.
Yeah, that's right. So you're just wondering what's power here? What is one? It's one for all of them. Okay. So then you just calculate 1 over 4 is z1 cubed. That's 1 over 4 is z2 cubed. Turns out to be negative I over 2 roots. Okay. So the integral over gamma sub r, as long as r is bigger than 1, the integral is going to be 2 pi over 2 to 2. Pi over root 2. Okay. We're not done yet, right? We still need to look at this thing. Right. So bz over z to the fourth plus 1. Right. CR, and we want to get some bound on it. Right? How are we going to bound this? How are we going to bound it? We have 1 over z to the fourth plus 1, right? How are we going to bound this? Well, you know, of course we could say, you know, right. But what bound do we get on this thing? Michael? 1, certainly that would be bounded by 1, but then we would have 1 times pi r, right? Which wouldn't be so good because as r goes to infinity, that goes to infinity, right? So that's not so good. Hold on for 1 second. Right. So we want to say like, let's find some lower bound on z to the fourth. Right. If we can find some sort of lower bound on this, right, then 1 over z to the fourth plus 1 is going to be less than 1 over that 1 over that thing. Right. So you want to find a lower bound for z to the fourth plus 1. So what's one way to do it? How much?
The r minus 1.
R minus 1? What's the bounded by R minus said bounded below. Is it true? Let me think. So, yeah, that'll work. That'll work. Why do you say, why is that true? Just explain it to me.
Because all the z's are on that semicircle. And wait. Yeah. Wait. I don't know.
You just thought it actually is true. But I think the way I'm thinking about it is going to be different from the way you came up with it. It's true, very good. Can anyone think of a way of getting a lower bound for this sort of thing? Right. You could one way is to use the opposite side of the triangle inequality. Remember that if you have a plus b, certainly it's less than this, but it's greater than or equal to the absolute value of the difference. So you could say, well, I know that this thing is bigger than z to the fourth minus 1. And so, the absolute value of z is r, right? So this equals, as long as r is bigger than 1, and we can assume that because r is tending to infinity, then you get r to the fourth minus 1, right? And certainly that's bigger than r minus 1, which is why I said you were right.
I was thinking like there's less than 1.
Oh, whatever. No, but r is bigger than
Yeah.
and r is tending towards infinity. Okay. In any case, this is one way to do it. So you'd say, okay, I know that this thing is bounded by 1 over r to the fourth minus 1 times the length of that semicircle. And as r goes to infinity, this goes to 0. So, right. So altogether, right, we end up with the integral over this thing plus the integral over the upper guy equaling pi over root 2, right, for r bigger than 1. Right? This is what's true. And then let r go to infinity. Right? And we see that this integral plus 0 equals that. And so half of it would be pi over 2 to 2. Okay, so our original problem turns into this one. Boop, boop, boop. Okay, let me sort of codify this, what we just did. Where is the I? The pi r comes from because we're integrating this thing over the upper semicircle of radius r, right? So it's going to be the upper bound of the integrand times the arc length, right? So this is bound on integrand, and this is the arc length. So, stated in more generality, if we look at this example and see what we used to get it, you can sort of codify it into a theorem. Say f is analytic on the upper half plane. Let's just say the closed upper half plane, say, with a finite number of singularities in the open upper half plane. So at this point, we're not allowing singularities on the real axis. Later, we'll allow, but we're not. If there exists an M, an R naught, and a P, where P is bigger than 1, such that f of z is less than m over z to the p for all z bigger than r naught in the upper half plane. Then the integral then I should say the principal value integral of f dx equals 2 pi I equals 2 pi I times the sum of the residues of the zi, where the zi are poles, are the singularities. Singularities in the upper half. Okay, is that clear that we can say that just from this example? What would happen? What's going to happen? Here's the key step, right? What's going to happen is we're going to try to bound this thing. We want to bound on the integrand. Well, your bound on the integrand is going to be 1 over r to the p, where p is bigger than 1, right? R to the p, where p is, you're gonna have some sort of bound like this, m over r to the 1 plus something, right? Multiplied by pi r, right? But that little epsilon is enough, right? Because then the r will cancel out the 1, but you've got this r to the epsilon on the bottom. As r goes to infinity, that's going to become huge. This whole thing will tend to 0, right? So this is what you need. Like you need this. One needs this sort of bound for where p is bigger than 1. So for example, if somebody is asking you about something like this, you can say, okay, well, I know that I can just apply this method, right? Because you have basically something next to the fourth on the bottom. Right? Or somebody gives you something like this, x squared x squared dx over x squared plus 16 squared. That's good. That's still good, right? You can apply this method, right? Because you've got a square on the top and a power of 4 on the bottom, so you can get some sort of whatever x squared value, right? And so you know immediately that you can approach these using this method. I was going to make you do it, but it's enough to know that a solution exists. We're not mathematicians.
Does that count for homework too? Just like
What's that?
a solution exists. Done.
It depends on the person, I'd say. Depends on the person. I may have told this story before, but there was a guy at Princeton who was just, sort of like legendarily smart. His name was Shin Mochizuki, and he was maybe a couple years ahead of us. And we heard that he was so smart that on his homeworks he would write, "This problem is trivial," and then the graders would give him full points for it because they knew that although this problem was probably impossible for everybody else, for Shin Mochizuki it was trivial, and so he just this is trivial, get full points. So he finished his degree. Yeah, so that's the answer to your question. It depends on who you are.
You mean given that you're at Princeton, the chance you'd be accepted for Princeton?
Okay, so okay, 5 more minutes. 5 more minutes. So yeah. So yeah, all of these tricks are sort of complicated. So so that's it for today. We'll stop. Yeah. So next time we're going to do integrals of the type you have some function multiplied by some trigonometric function, and these sorts of integrals arise in when you're talking about the Fourier transform. So it's not at all, as I said last time, a contrived problem, but a very natural one. This arises. This is actually something of real concern. Okay. So and things will get a lot more subtle next time.